At this point, I would like also to mention that once you use those DFM tools to pinpoint and find which matching network is causing the yield problems in your design, there is another tool in ADS that will help you find a low-sensitive matching network or a high-yielding matching network. This tool is the matching utility tool in ADS. So you do have another tool that could assist you find the right matching network for your design. You see, when you process an amplifier in the foundry, if the process is under control, the outcome of the foundry, when you measure the wafer, when you probe the wafer for all these amps, they will show a curve, a normal distribution curve like the one I show here. With a nominal gain, most of the chips will have a nominal gain of 20 dB, but some of them will go down all the way to 17 and all the way to 23 dB. So this is the plus or minus 3 sigma of the process. And I made those numbers just for illustrating to you and this example. So we have the plus or minus 3 sigma 6 dB variation and the nominal gain of 20 dB. Now, if my specs are between 14 dB and 26 dB, which usually doesn't happen. I mean, you know, this is a really wide spec. So if my specification is your amp has to be between 14 and 26 dB of gain, then I'm fine. I got 17 to 23, the plus or minus 3 sigma, which is 99% or of my chips meet the specs, so I'm fine. You know, I get an amplifier that is used within my spec range, 14 to 26. But unfortunately, this usually doesn't happen. The specs usually are much tighter. The specs designers get are something like the gain has to be between 19 dB and 21 dB. And if your amp, the one you designed, have a distribution plus or minus 3 sigma between 17 and 23, then you have many failed parts. All these parts are failed on the left and on the right of the spec lines. So what do I do to my design to make it meet the specs with much higher yield, like 100% yield? What do I do with this amplifier? I cannot change my specs. The specs are 19 to 21 dB right here. What can I do to this curve to make it become much higher yield with this spec? One way to think about it is if we squeeze this curve, if we make it much narrower inside the spec line. So basically what I'm saying is like we squeeze this curve and try to squeeze it more and more to make that normal distribution curve lie within the specs or inside the spec. This is what will help us achieve the much higher yield and consistency and lower sensitivity design. And just to illustrate this concept with the amplifier that I showed you before, if I take this amp, the standard amplifier, and the DFM based or the design of experiment based amplifier 2, and I plotted the gain on the x-axis, so basically amplifier 1, which has a wide variation here in the gain, I can plot it with this normal distribution curve, and I take the DOE based design and I plot it here on the x-axis with the gain on the x-axis. Notice the difference. Amplifier 2, which is the DFM or DOE based, is much narrower and tighter than amplifier number 1. Even if I take amplifier number 1, this wide curve, and I design center it, move it to the right to meet my specs or to have more gain, the curve will still be wide and it will still be sensitive design. maybe over temperature or voltage supply variation, it will shift and you'll lose many of those chips in yield if you keep that design as wide as it is shown here. So the best way is to achieve that tight distribution curve. And how do you do that? It is by using those DFM tools that will help you find where the problem is. So the DFM design process, you start with a design, whether it is an existing design you have or a new one. And maybe the first step when you do yield analysis, you see that red curve. It's very wide distribution. It's sensitive design. What you do, you use those DFM tools, which I will show you next. And the DFM tool will tell you what components to fix or what matching networks. And slowly you can convert your design into a very tight, with tighter distribution, just like it's shown in curve number 4 in green. And finally, once you have this robust design, you want to do a final optimization in the yield or design center it. You can shift this into this curve, into the pink curve, to center it over your spec, whatever spec you have. But the design quality, you can see it is very tight, it is not sensitive, and it will withstand the process variation, the temperature variation, and the voltage supply variation. It will be a rock solid design. This is the art of doing DFM or robust design in MMIC. So again, I repeat, yield analysis, many people think yield analysis is part of statistical design and making robust circuits. No, this is not true. Yield analysis is nothing but a check to check whether your design is going to have high yield or low yield, or whether your design will make a first pass success or not. It does not fix your design. It does not transform your design into a robust circuit. So Monte Carlo yield analysis tells you there's a problem. Then these tools in ADS, design of experiments, will help you pinpoint, tell you exactly where the problem is in your design. Sensitivity analysis, sensitivity histograms, extracted, all these histograms are extracted from this yield analysis, which is post-processed the data in such a way that it will help you find a lot of information about your design by using those sensitivity histograms. Here's an example of the sensitivity analysis. Sensitivity analysis of your circuit takes few seconds to generate. We have absolute sensitivity and normalized sensitivity in ADS. So for example here, it is easily shown that the output matching network resistor R1, the gain drops 0.25%. It is showing 0.25 here on the y-axis for every 1% increase in R1. So it tells you that by looking at the plot that R1 is the sensitive component here, and this is how much the gain drops relative to R1. But sensitivity analysis is localized. It doesn't take into account the interactions between elements. It's one component at a time doing that analysis. This is why you have to go beyond sensitivity analysis and use the design of experiment tool and the yield sensitivity histogram tool, which accounts for all the components interacting together. As I said before, yield analysis indicates whether or not there is a problem with the yield. The design of experiments and the yield sensitivity histogram tools are like the X-rays. They allow us to find exactly where the problem is in the design, and it will help us fix the problem by knowing exactly where it is.